Yeah. I'm not.
You didn't get it. No. Yeah, I didn't.
That's why I thought you weren't here. That's why this is old. Usually I put the old and the new.
Okay, but these are from today.
Okay, so day 2. So I'm going to sort of continue. I'm going to finish I'm going to talk about physical changes and chemical changes, because there are 2 kinds of changes that can happen to matter. Oh, before I get into that, I just want to make sure there's 2 new handouts. There are folders by last name. Most of you have already picked up the handout of the day that you did last time. But also try not to forget to give me the academic honesty statement signed. You can do that after class or next class. We're having I believe we have a quiz a week from today. So we should have it signed and handed in by then. Anyway, okay, so I'm going to talk about physical and chemical changes. These are different types of changes that can happen to matter. And anyway, what are they? So physical changes are ones where they're basically changes in state. So for example, solid to liquid to gas. But when you go from solid to liquid to gas, or gas to liquid to solid, or any of those changes, you don't actually change the identity of the molecule or the atoms. And, you basically have the same molecules before and after. So for example, if you have water going from a solid to a liquid, basically melting ice, it's still H2O, it's still water molecule. So that's what we call a physical change. I got it. You don't have to tell me that. So the thing about physical changes is they're very easily done and very easily reversed. So these are easily reversed. And that's not true of chemical changes that I'm going to do in a minute. But there's another sort of less obvious state of matter. And that is dissolved. So a lot of times in this class, we have compounds that dissolve in water, and we call it something. So dissolved in water. Anybody take a high school class where you might have put a parentheses next to something in a chemical equation and write AQ in it? Does anybody remember that? Heard of that? I know I was talking to someone before class. So dissolved in water, we call the aqueous state or the aqueous phase. And so going from, say, taking sodium chloride, right? NaCl, sodium chloride, and in the solid state and putting it in water, you end up with aqueous sodium chloride. So the act of dissolving is also a physical change. That delta, I don't know if you've seen that before, but we in science always use a delta for a change. So physical change would be that delta is what we use. So I just want to show you a picture. Here's a picture. Whoa, this isn't it. I think I'm in the wrong place. Oh well. Stuff happens. Let me fix this. So my notes don't get mixed up. Sorry about that. Okay, oops. Okay, so this is the picture I was looking for. So this shows, okay, we have sodium ions, chloride ions. So this is a compound here, this solid here. This is sodium chloride. And you could see that you have, so the way sodium chloride exists in solution is it has chloride ions, which are negatively charged ions. So it exists as an ion, it has a charge. This is not a topic of the current chapter. We'll be doing this in a later chapter, but just to describe what it is you're seeing here in this picture, you have a chloride ion. This here is a positively charged sodium ion. That's how NaCl exists. And it's got these side-by-side ions where all the negatives are around positive charges and all the positives are around negative charges. And here you have your water molecules. Again, we use red to represent oxygen and white represents hydrogen. And so you see this H2O molecules. And so now you see this crystal of sodium chloride sort of breaking up as these ions each get surrounded by water molecules. And this is the process of sodium chloride going from solid to aqueous. And really what it is it breaks up into these ions that are attracted to water molecules, which is something we learn about later. Here we have another process of dissolving. And this is sugar. Now, sugar is a much bigger molecule. Well, sugar is a big molecule. You can see it's sort of pictured there. Its formula is here, and maybe you know this formula from other things. You know what? I'm going to shut this light out right on top. Yeah, right? Well, I think I'm okay. All right. So what happens when you dissolve sugar is similar, except sugar is not charged, doesn't have charged ions, but the sugar molecules become dispersed in the water, and we would write it as C12H22O11 solid goes to C12H22O11 aqueous. Okay, so again, we have sugar dissolved. Now, big difference here, sodium chloride is what we call an ionic compound. And sucrose is a molecular compound. So sodium chloride actually does not consist of molecules. It consists of positive and negatively charged ions, but that's a topic, like I said, and I believe the next chapter. So I said that when you have a physical change, you can easily reverse that change. So it's pretty easy to dissolve salt or sugar in water, but how do you reverse the change? How do you go the other way, right? So NaCl solid, put it in water, and you get aqueous NaCl. But the question is, can you so easily go in reverse? Boil it, right? Yes, that's right. But we call it a distillation apparatus. So here's a distillation. I gave you a picture of this in your packet. Okay. And what you do is you boil, heat up basically the solution of salt water. The water goes to the gas phase, it rises. It ends up in this condenser, right? The steam is rising and it goes this way. Now the blue in this picture here is showing that water is flowing on the outside of a tube that has an inner tube that contains the gas. And we call this a condenser because it condenses that gas. And what happens is you end up with drops of water falling in here. And so here you end up with pure water, which they call distilled water in this picture. But where's the salt? How do you get the salt back? Where is it? Yes. Yeah, it's over here. It ends up, the salt remains here. And that would similarly would happen with the sugar, although the sugar would probably burn pretty quickly after that happened. But anyway, the salt remains here, and that's how you're able to separate them so easily. So, so yes, you can reverse these physical changes. The other way, for example, I don't think I said this, but solid to liquid of water, you would have to heat this. How would you go from liquid to solid? You would have to cool it. Okay, so these changes are quite reversible. Now that's really very much in contrast with chemical changes that's the other type of change that I wrote here. Okay, chemical changes I'm going to talk about now. Chemical changes are very different because a chemical change produces a completely different substance. Really very different. So, and it happens in a process, that we call a chemical reaction. And this course is full of chemical reactions. So it's important to get familiar with them and to know, what they're like. So here's an example. Here's an example, iron reacting with oxygen to produce iron oxide. Okay, anybody know what the common name of this iron oxide is? Rust, exactly. I write it in red because it's kind of orangey, right? And that's my point here in using this example is, so here we have a metal. As a metal, it's pretty moldable. It's pretty malleable. I mean, you might have to use a lot of force to do it, but you can mush around iron. But you can't do that with rust, because instead of being malleable and formable, rust is actually very brittle. So you have very different properties because you have a completely different substance. Let's see, for example, also, because iron is a metal, it conducts heat pretty well. You use cast iron pans at home, okay? If iron oxide is not conductive. So that's examples of different properties. Of course, here, this is a gas. It's colorless, it's odorless, and nothing here resembles a gas. Okay, so that's just an example of a chemical reaction. Here's another example. Somebody maybe could tell me what this is or what it's called. That's a capital O, just want you to know that. Anybody know what this reaction is called or recognize it in any way? Well, it's it's actually the reaction of photos. No, it's the opposite. Yeah, you're right. But that's right. But we call it combustion. Yes, you're right. But you don't actually metabolize methane. But yeah. So, plants go this way, except they don't produce methane. They produce other organic chemicals. But this is actually burning of methane. Okay. And when you do this, well, when the body does something similar, it produces ATP and stuff like that. But when you just do it, say in your kitchen, when you turn on the gas in the stove, you start with methane, which is CH4, which I could write this way, showing the bonds, and oxygen that's attached to another oxygen. And you end up with carbon attached to oxygen and hydrogens attached to oxygen. So what I'm showing you here is that the atoms are completely rearranged. And that is also typical of a chemical reaction, that you have completely different atom rearrangements in products than you do from reactants. Here you can see the hydrogen is bonded to oxygen, whereas here the hydrogen is bonded to carbon. Here oxygen is only bonded to itself. Here you have oxygens bonded to carbon and oxygens bonded to hydrogen. So it's a complete rearrangement. Can anyone tell me what I've sort of left out of these equations that we'll have to consider when we do the stuff later in the course? So this is not really a complete equation here. What's missing? Well, should I tell you, or are you going to tell me? Come on. How many carbons do you have on the left? You have one. How many do you have on the right? You have one. How many oxygens do you have on the left? And on the right? 3. Yeah. So there's a law. It's called the law of conservation of mass. And basically it leads to the fact that you have to have the same number of atoms on each side of the equation. So you would have to balance this equation. And balancing is another topic that we talk about later. So I'm not going to do much about it now. But to balance the equations, you would have to put what we call coefficients in front of each of these formulas to make sure you have the same number of atoms of each type on each side of the equation. Is there a question about that? Okay. So we have 2 types of changes, chemical and physical. And we also say that there are 2 types of properties that chemicals have, that substances have. So those 2 types of properties have the same names. They are physical properties or chemical properties. And a physical property are those that a substance displays without changing its identity. Just like a physical change is a change a substance makes without changing its identity. So a physical properties are those a substance displays without changing its identity. What is an example of a physical property? Something you could just tell. Well, wait a minute. Yes, I guess you could call, but you wouldn't necessarily say that temperature is a property of like this podium. I guess it is. I guess I would have to give you that. But I'm not going to write it down because I don't like it. Give me another one. Color. I like color. Things like size. Yeah, that's true. Yes, you could say whether it is a solid, a liquid, or gas. How about something a little more technical, like boiling point? Now, you could tell the boiling point of something. That's when the big bubbles start to form, right? You could tell the boiling point of something without changing its identity, because when you go from liquid to gas, you're not changing its identity. So therefore, boiling point is a physical property. Another thing is, say, density. remember what density is, right? That's mass over volume. You could certainly measure the mass without changing the thing. You could certainly measure its volume without changing it. So therefore, density is a physical property. Another thing would be like conductivity. That's what identity means. Identity has to do with the molecule that it is. If it's H2O as a liquid and H2O as a gas, it hasn't changed its identity, right? Conductivity is something, you could see how well it conducts by heating it up, but that doesn't change its identity. So that doesn't change. That's not a chemical change. So that's another example. Chemical changes, these are the really interesting ones. Chemical changes are shown or displayed when a substance reacts and changes its identity. In a chemical reaction and changes identity, because that's what happens in a chemical reaction. Okay, so let me give you some examples. You're out on the grill and you're using a propane grill. So propane burns. Is this chemical or physical? That's chemical, right? Because a propane, like the methane in the combustion equation, is going to produce new substances, carbon dioxide and water, okay? What about, how about this one? Paint dries. Paint dries? What's happening when paint dries? Oh, I see what you're thinking. But in fact, you start with a liquid, right? But what happens is not that liquid forms, that liquid is not freezing. What is it doing instead? It's what does that mean though? Yes, Beck. It's evaporating, right? So it's essentially evaporation. So that is a physical change. So sometimes it could be a little tricky. How about this one? You make a cake and you have a batter, and that batter cooks. You're going to bake a birthday cake for somebody. Yeah, how do you know that that's chemical? What is how can you know for sure that you've created a new substance? You're mixing all kinds of substances together. It's really just, yeah, but well, heat can be applied to go from solid to liquid. What new substances form that has a different property? What's in the bread? Well, the eggs get denatured. That's a totally, but what forms when you bake a cake? What makes it light? The air. Yes, the bubbles that form from the baking process. So that's what I was kind of looking for anyway. So that's definitely chemical, because you get bubbles, air, that's actually carbon dioxide bubbles form, and they make the cake nice and light or whatever. But that's evidence. That's all you need, really. You have evidence that you have a substance there that wasn't there before. So that's a chemical change. What about this one? What's evidence? A good evidence, really good evidence of a different substance is what happens there. Can you speak up?
Whiter.
Yeah, so in other words, a stain, which maybe was red, goes to white. Okay, so you have a color change. So this color change indicates a new substance. And how about this one finally? I really didn't have enough room. I got to make a little more room. And how about this one? Dry ice forms a gas at room temperature. Anybody ever seen dry ice? You know what dry ice is? It's something that's used to cool or freeze things. It's actually solid carbon dioxide. They use it in shows and stuff. When you see that mist on the stage, you know, you would go to see The Tempest or something like that, and they're trying to show something very mysterious. Anyway, so dry ice, which is solid carbon dioxide, forms a gas. What is the gas? Anybody know? It's carbon dioxide at room temperature. So this is a physical change, even though it looks kind of cool. So I'd like you to do this part of the handout of the day. This is also activity 4. But do it on the handout of the day. And I want you to circle the physical changes and underline the chemical changes. Unfortunately, some of these things like toasting marshmallows are on different lines, and water boils. So some of these things aren't chemical or physical changes, okay? Just pick out the changes and do that. If you have a handout from last time, you can get it in the folder under your last name. From last time. If you have a question, you can ask me or ask the person next to you, or what's your question? I have a little more time. Everybody doing it. What's that firefly? Yeah, I don't really expect you to know that. But that's called chemiluminescence. That process. What happens is there's a chemical reaction in the firefly that produces light. A chemical reaction produces light. It's called chemiluminescence. I think they actually call it bioluminescence because it's a biological reaction. So
Is that what happens?
what?
Is that what happens? So, on the water.
Glow. You're talking about the glow.
Yeah.
Bioluminescence. It's some reaction in the critter that produces light. Are you done with this? Somewhat. Well, I don't collect it till the end, so you can have you know, you can change it later if you change your mind. No questions about it? All right. Okay, then I am going to move on. I'm going to move on then to measurements, which is everybody's favorite topic, including unit conversions and significant figures and things like that. So in chemistry, we use units that are in the SI system. This is called a system. This is an international system. It's System International. You don't have to know that. Nobody cares. we're really talking about the metric system. And if you have a question, please ask it. Otherwise, just, try not to talk when I'm talking, because I can hear you. Hello back there. Hi. Yeah, no, I could hear you, so it's very distracting. If you have a question, please ask it. You have a question? All right. Okay, so we use the metric system, the SI system, the typical length, the base unit. So the metric system is based on base units. The length is the meter, which is a little more than a yard. I write greater than, about, equal to a yard, so it's a little more than a yard. Mass is another common unit that we use, the gram. 454 grams are in 1 pound, so you get an idea. It's a pretty small mass. And time, we all know what a second is like. I don't have to tell you, it's the same in the system that we use, so we don't have to go over that. But the thing about this metric system is that almost every country uses it except for ours and Britain, and maybe some former British colonies, but no one else uses it. So the metric system is really used all over the world, and all scientists use the metric system. So we have to use it as well. And it's a good thing to know about when you travel. Anyway, this metric system has what we call prefixes that change the size of units and make them more convenient. So I'm just going to give you an example, or a couple of examples. So here's one. The distance, this is the distance by car. I use Google Maps to do this, to go from Providence, Rhode Island to Los Angeles. I actually picked my address, and my son lives in Los Angeles, so I use his address. And actually, it's a lot of meters. It's 4,342,000 meters. Okay, I rounded it to the nearest thousand, and I should know because I drove that this summer. So I drove across the country this summer. It's quite an experience. I hope that you get to do it sometime in your life. It was amazing. I visited people I hadn't seen in 30 plus years. So, you guys weren't even born yet when I met those folks. But anyway, it was a lot of fun. And anyway, if I said, I drove 4,342,000 meters, it's like, what the hell is that? It's just like too big a number, too cumbersome. So we would convert it to kilometers, and in kilometers, it would be 4,342 kilometers, which is a much more handleable number. Now, of course, we're not familiar with that number either because we use miles in this country, but it's about 3,000 miles, so you can get an idea that there's a little, like almost 2 kilometers in a mile. But that's not what I'm trying to tell you. What I'm trying to tell you is that when you put a prefix on that meter unit, you make it a size that's sort of more amenable to the thing you're measuring. It's more convenient, okay, to talk about 4,000 kilometers than to talk about 4 million kilometers. Another example for something very small would be, for example, a bond length. So a typical bond length. So what does that mean? That's how long a bond is between two atoms. Now it varies from bond to bond, but a typical bond length is like this. Let me write it down. I'm going to have to write 9 zeros after the decimal point. And if I use meters, that's what I have to express it as. And that is really inconvenient. So I'm not going to express it in meters. I'm going to express it in nanometers, or NM, okay? And 1 nanometer is 10 to the negative 9th meters. That means 0.0000008 of these zeros with a 1. It's that many meters. I forgot to tell you that 1 kilometer is 1,000 meters, okay? But 1 nanometer is 1 times 10 to the minus 9th, or 10 to the minus 9th meters. And if I express this number in nanometers, it becomes 0.15 nanometers, which is a lot less cumbersome a number than 0.00000000015, right? Because you could lose one of those zeros. So that's how we use these prefixes. And here they are. Here's a table, which I gave you, so you could turn to that page if you want. Now, some of these I think you should know, like you should memorize, not very many. I would say that you should memorize milli, centi, micro, and kilo. So you should know that. What happened there? You should know that one micrometer is 1 times 10 to the minus 6 meters. We would also could write it this way, or we could write it as 0.00001 meters. Okay, so milli is just 1,000. So it's 1 times 10 to the minus 3rd meters, or 10 to the minus 3rd meters, or 0.001 meters. And similarly for these other ones, I'm going to do some examples so we'll get a little more familiar with this. So that's conversions within metric units that we will be doing, and I'm going to do some examples. But they're also, we also do conversions from British to metric units. And I just have a couple of examples in this table. Okay, so this talks about going from how meters relates to yards. So you could see I had told you a meter was a little bit more than a yard. It's actually about 1.09 yards. And also it talks about going from liters to quarts, inches to centimeters, things like that. So we have to learn how to do these unit conversions. And this, I'm sure, is a topic that you've seen before in high school, but I'm going to talk about it again so you can maybe learn a new way to do this. Or maybe you already do it this way. So when you convert quantities from one unit to another, you need to use conversion factors. And it starts by writing the unit, how one unit depends on another in the form of an equation. So for example, I write 1 kilogram equals 10 to the 3rd grams, or 1 kilogram is 1,000 grams. Okay, now I'm just going to show you this once, so you don't have to do this every time, but I could divide both sides of this. This is an equation, there's an equal sign. I could divide both sides by 1,000 grams. Okay, and when I do that, what is the right side of this equation equal to? That's 1, all right? So that equals 1. So that means that 1 kilogram over 1,000 grams is equal to 1. And that means that I can multiply anything by that quantity, and I'm multiplying by 1. And when you multiply something by 1, what happens? It really doesn't change. The quantity doesn't change. Only thing that changes is the unit. Okay, now I could have done this the other way as well. I could have had 1 kilogram equals 1,000 grams. And instead of dividing by 1,000 grams, I could divide both sides of this equation by 1 kilogram. And now that is equal to 1 as well. So that means that this thing is also equal to 1. So both of these, which we call conversion factors, equal 1. A lot of times we call this, we call it sometimes an equivalence ratio, because what's on top is really equivalent to what's on the bottom. And when you have an equivalence ratio like this, you can always multiply by it, and you're not doing anything illegal mathematically, because essentially you're multiplying by 1. Okay, so we also call this equivalence ratios. Okay, so now we know that. Let's do activity 5, number 1. All right, so here's activity 5. We have a simple conversion. You know, some of you in the class probably find this very easy. Some of you have a good background, some of you have less of a background. I'm really doing this to try to show everybody how you do it. But if you're bored, you know, I have a whole sheet here of extra problems that you could work on your own while we're doing these. These are problems for practice, things like that. I know that some of you already know this, but a lot of you don't. So I'm going to go over this in this much detail. So if I want to convert this from grams to kilograms, okay, so I need to make a conversion factor that relates grams to kilograms. And that's the conversion factors that I've just talked about. But we have two different ones, right? We have this one and we have this one. And I'm going to write those down. So there are really two possible conversion factors. One of them is 1,000 grams to 1 kilogram. We know that this equals 1. We also have the other way with 1 kilogram on top. Okay, now I'm going to use a method that is called dimensional analysis. I don't like to think when I do a unit conversion. I don't want to think, oh my God, do I have to multiply here or do I have to divide? Because students get that wrong all the time. So I want you to use this method because it is honestly foolproof. Okay, all you have to do is say to yourself, if I want to cancel grams, how do I write this conversion factor? You have a grams on top here. You want to be able to cancel with grams on the bottom. So this is the conversion factor that you use. Okay, and you notice that the gram units cancel. Now, sometimes this happens to me. I write the conversion factor the wrong way. Now, what if you write this conversion factor the wrong way? What happens? Supposing I did 17,321 grams, and then I put in 1,000 grams to 1 kilogram. I would do that. And yes, what would I then say to myself? Yeah, the grams aren't going to cancel. The unit of my answer, and you have to remember that units work just the way everything else does in a mathematical expression. I will end up with, 17,321 times 1,000, and my units will be grams squared per kilogram. Well, I don't know about you, but that's not what was asked. Doesn't make logical sense to end up with some crazy unit like that. So that tells you that you did it wrong. So you don't have to think, do I multiply or do I divide? You simply write the conversion factor so that the units cancel. Now, of course, if you wrote 1,000 kilograms per gram, that's going to be wrong. And that's going to get you the wrong answer. So it's not completely foolproof, but it really helps you if you do it this way. Now, a lot of students didn't learn it this way in high school, so they don't do it. And I think it's a big mistake. I think you should adjust it now and start doing it this way. And you, of course, you end up with 17.321 kilograms when you do it that way. That's the answer. Okay, so I hope I'm convincing you that using dimensional analysis really makes your job easy. We do a lot of conversions in here, grams to moles. We'll learn about moles to grams. Students say, do I multiply or do I divide? And I'm like, use the units. The units are going to tell you. So I highly recommend that you learn this, okay? So how about you guys, let's do number 2, kilograms to grams. So 0.0273 kilograms to grams. So which one of these conversion factors do I use? $1,000 grams, 1 kilogram. Okay, so you could see now what I'm essentially doing is multiplying. Here, what I did, because 1,000 was in the denominator, I took 17,321 and I divided by 1,000. Here I'm taking 0.0273 and I am multiplying by 1,000. Okay, but I didn't have to think, do I multiply or do I divide? And let me tell you, there are times when I convert moles to grams or kilograms to grams or something like that, and I do it wrong. And I just say, oh, and I flip it over and I do it right. So I really think this is the way to go for you. But anyway, really in this class, what matters is that you get the right answer. And if you have a better way of doing it that you like, obviously I accept that. But when problems get harder, it becomes much more cumbersome if you don't use this type of method. So I want to tell you here, we have a HOD question, and I want you to convert 42.5 milliliters to liters. So look at the handout of the day. And here is the equation that you start out with that leads to a conversion factor. Now, there's going to be 2 different conversion factors, right? What's one of them? What? And what's the other one? So you start with 42.5 milliliters. You put a big parentheses, put it in so that your milliliters cancels. So the unit you want to go away is on the bottom of the conversion factor. And then do that and finish that problem for me, please, on the HOD. Yes.
There's a little piece. All right, so now I think if anybody have a question. All right. All right, so I'm going to move on to a slightly more difficult problem. So this one, it's actually a lot more difficult in some ways, is to convert 4.27 times 10 to the 4th micrograms to kilograms. All right, now a microgram is a very tiny unit, right? 1 microgram is 1 times 10 to the minus 6 grams. Okay, that's a Greek letter mu that we use for micro. So a microgram is much, much smaller than a gram. It's a very tiny unit. And so what's harder about this problem is that I know how to convert micrograms directly to grams, but I'm not asking for grams. I'm asking for kilograms. So this is kind of a 2-step problem because there's no direct conversion in a chart between micrograms and kilograms. So how do you think I'm going to handle this problem? Yes. Yeah, I'm going to go from micrograms to grams in the first step. And then I'm going to go from grams to kilograms in the second step. Okay. Now, this problem does involve scientific notation, and I want to make sure that everybody in this class knows how to use scientific notation on their calculator. Okay. So, take out your calculator. First of all, let's figure out what we're going to do. We're going to go from micrograms to grams. 4.27 times 10 to the 4th micrograms. Now, what is going to be in my parentheses if I go from micrograms to grams? What am I going to put on top and what am I going to put on the bottom? Well, wait a minute. Let's talk why we're doing. So micrograms is here. So we want to cancel micrograms. So micrograms has to go on the bottom. And grams will go on top. And that way our microgram units will cancel. So we know that 1 microgram is 1 times 10 to the minus 6 grams. Okay, and if you don't know that, you go back and you look at this chart. And here you see that micro, 10 to the minus 6. They give an example here. 1 microliter is 1 times 10 to the minus 6 liters. But it doesn't matter whether we're talking about liters or grams. It's always that same 10 to the minus 6. So now you have to multiply 4.27 times 10 to the 4th by 1 times 10 to the negative 6th. Every one of you has, I hope, a calculator with you today, and I would like you to try to do this on your calculator. Now, first, before you start, I want you to look for a symbol on your calculator. It might say EE, it might say EXP. On this guy who came up to me before class, he has a key that said times 10 to the X or something. What did it say? Times 10 to the X, right? Is that what, who is the guy who came up to me before class? Did it say times 10 to the X?
Yes.
It is working, come on. Oh, well, just start from the beginning. So when you key in this times 10 to the 4th, you on a graphing calculator, this is a second function. So it's in the little writing above one of the keys. So you key in 4.27 EE. This EE means times 10 to the. That's what it means. And then you would put in 4 for times 10 to the 4th. And then you would hit the star for times 1 times 10 to the. Now, some calculators, you put the plus minus before the 6th, and some calculators, you put it after. And let me give you the right answer that you should get. And I want to make sure everyone in this class gets this answer. 4.27 times 10 to the negative 2, or 0.0427. That's what happens when you cancel. So I'm going to walk around because this is very important, because students use their calculators incorrectly all term long in general chemistry, all year long. I correct students in Chem 104 in April that don't know how to use the EEP on their calculator. And let me tell you that you run into a lot of problems if you don't use the. And by the way, that thing means times 10 to the. So don't put times 10 times 10 to the, then you'll be multiplying by an extra 10, okay? So just do it right, all right? Ah, the carrot. We love the carrot. You understand? Yeah. Okay, the reason why it's not good to use the carrot happens if you happen to actually dividing by a number and you use the carrot. Don't use the carrot. Let me explain that a little bit. All right, so people want to use this carrot. All right, this is what happens if you use the carrot. If you take the number 17 and you divide it by 3 times 10 to the fourth, and you use the caret, and you key this in, you key that into your calculator. So the right answer to this problem is 5.67 times 10, or let's say 5.7 times 10 to the negative fourth. That's the correct answer. If you do it 17 divided by 3 times 10 to the fourth, you get a completely different number. Okay? Why? Why do you get that number when you use the caret? Yeah, what it's doing is it's taking the result of this calculation. It's taking 17 divided by 3, and it's multiplying that, and then divided by 3, and then it's multiplying by 10 to the fourth instead of dividing. So you would have to put a parentheses around this. And that is a whole lot harder than simply dividing by 3 10 to the fourth. So I don't recommend the caret, although the caret works in a lot of times, but not when you're dividing and not without using parentheses. So yes, getting back to this, I want to make sure that you are getting this answer. Yeah.
I have it. But I no, I know, but I haven't.
Yes, a lot of graphic calculators, it's parentheses, but it's perfectly fine. I just want to make sure that whatever calculator you use, you get the answers that I have here in this box. So I want to come around and have you show me what you're doing if you're getting the wrong answer. So anybody getting the wrong answer? No, that's the answer.
Oh, yeah, we don't have to change the.
Well, we're not on the first step. We're on the first step. You get the right answer. That's the first step, good. All right. Well, let me go get my, just to make sure. This is my chance. Yeah. Yeah, if you do the whole thing, so I'm just gonna give you the answer to the whole thing. So the answer to the whole thing, this is an aside. Answer to the whole problem is 4.27 times 10 to the negative fifth. Now, if you can do that by moving the decimal point, more power to you, honestly. But if you might get a wrong answer. So be careful. Get the right answer. Then yes. Get it?
I think what you were saying was you went, you had it for her out, to have it, but I don't know if you had it. Before to have it. Yeah, right. Once you are all of the No, kilograms. I like it. The answer to the first part of the problem. As far as we are, and that's one of the reasons I have a zero. But then you did the next step. At 4.2, that was my that is the answer to when you heard the whole thing. No, it's not. It's not. I just really want to make sure you're calculating.
So this is just an aside. So let's continue with this problem. We had 4.27 times 10 to the fourth micrograms, and we multiplied by 1 times 10 to the minus 6, grams. So we see micrograms will cancel. So we have to do this math now. And I believe that everybody in here is okay with this now. So you might have seen that number, or 4.27 times 10 to the negative 2. Those are equivalent. They're both correct. That's perfectly fine. But now we have to take the 0.0427 grams and we're going to convert it to kilograms. So we have to use how many grams in a kilogram, or kilograms in a, how do we do this? Where do I put the 1,000? Or, you could do 10 to the 3. Yeah, so it was different ways of doing it, but this is the easiest by far. And you get 4.27 times 10 to the negative 5th kilograms, okay? And also I want to tell you that if I were doing this problem, I would do it all at once. I would start with 4.27 times 10 to the 4th micrograms. I'd go, okay, we have 1 microgram is 1 times 10 to the negative 6 grams. that if I do the math right there, I'll get the 0.0427. If I stop here, I'll have grams, but I don't want to stop there. I want to continue and say one kilogram is 1,000 grams. And when I do the math here, I get 4.27 times 10 to the negative fifth. And you could do it all at once, which would basically be taking 4.27 times 10 to the fourth times 1 times 10 to the negative sixth and dividing that by 1,000. You could do it all at once, but you don't have to. Yes. -5. Now, let me ask you something. When you're keying, when you're putting in, are you using the EE key? Are you doing times 10 EE? You're just doing times, you're doing EE, not times 10 EE. I'm just wondering why you're off by a factor of 10, because you are. Sometimes what students do is they think, for example, 4.27 times 10 to the fourth, they might key it in as 4.27 times 10 EE fourth. That would give you an extra factor of 10. This shouldn't be here, right? Because this means times 10 to the. So, but this right, this is the right answer. If you want, we can look at that after class if you have a few minutes. Okay. All right. Okay. So I hope that we've at least begun to solve some of those calculator problems. Okay, let's go on. The next problem I'm not going to do, I'm going to ask you to do it at home, and that's a conversion, which is activity 5. Let's see. Yeah, activity 5, number 4 is a pretty simple conversion, inches to centimeters. And you would use the fact that you have 2.54 centimeters to 1. Well, there I did it anyway. And you get 43.9 centimeters. So that's pretty straightforward, much more so than the previous problem. So what I want to do now is go on and this is we're going up a notch a little bit, up the ladder. The next stage of difficulty is when you convert what we call derived units. So these are when you're not converting base units, you're not converting just length or meters or grams or something like that. When you're actually using a unit that's based on those units. So here we have volume in this problem. And volume is length times width times height for something that's rectangular. But when you have a volume unit, you have a length cubed. Okay, so you have to be a little more careful when you do your conversions. So here is a problem to convert from cubic meters to cubic centimeters. Now, a cubic meter is a meter on every side. It's a pretty big unit of volume. A cubic centimeter is a centimeter on each side. So I have this number of cubic meters. So my first question is, when I express that same number in cubic centimeters, is the number going to be bigger or is it going to be smaller than cubic centimeters? Cubic centimeter is much smaller than a cubic meter. So you need many more of them to describe the same volume. Does that make sense? Yeah. So you're expecting a much bigger number of cubic centimeters. Yes. If you happen to know that, yes. But I would guess that there are very few people in the room that know that. And it's very easy to make a mistake, right? So this is what I do. I don't know how to go directly from cubic meters to cubic centimeters, but I do know how to go from a meter to 100, that's 100 centimeters, right? A meter is 100 centimeters, or I could have done it this way. 10 to the minus 2 meters is 1 centimeter. But I prefer, it's more intuitive to me that I know that 100 centimeters is a meter. So I much prefer this way. Okay, now, can I just multiply like that and be done? If I just tried to multiply these two things, I know this is a conversion factor. I know this equals 1, but I'm not going to be able to cancel the units, right? So what do I have to do to this conversion factor? I have to cube it. I have to put a cubed here. So what that really means, I'm going to be hopefully very clear about this, is I take 0.00125 and I'm literally multiplying by this conversion factor 3 times. You don't need to write this. Or maybe you need to write it once. But you're literally cubing the conversion factor. And so that is how you are able to cancel the cubic meters. So, if you just write it this way, it's fine, as long as you remember that you got to cube that 100. Okay. And I think most of you have on your calculator something like y to the x or something like that. And so you could multiply by 100 y to the x3. That's 100 cubed. Or, you could just multiply by 100 times 100 times 100, as long as you do it 3 times, and you end up with 1.25 times 10 to the third cubic centimeters. Okay. So that's the answer to that problem. So that is a little bit harder when you have a derived unit. Now, there's a next problem on the sheet is problem 6. And I am going to say that this is really, we never do this. General chemistry, I will never ask you to convert one density unit to another density unit. I think problem 6 is a little too hard for us today. So I'm going to make it a special problem. You can hand it in Tuesday for extra credit. It's really optional. If you don't like math, don't do this problem. It's just not for you. Okay. All right, so here is another example of converting a derived unit. Area is length times width. So what I'd like you to do on the handout of the day is to start with this square centimeters squared, and convert it to inches squared. Okay, and so now what are you going to have to do this? Where are you going to put the 2.54 centimeters, and where are you going to put the 1 inch? And what do you have to do to that conversion factor? That's what I want you to do next. Are there any questions? I can't hear you very well. Yeah. So let me take a look. Okay, so you're basically dividing by something. Let me ask you, is the number gonna be bigger or smaller than 56.5? Smaller, sure, because, and square inch is bigger than a square centimeter. Okay. All right, I'm gonna move on to everybody's favorite subject in general chemistry. And that is significant figures. Yeah, everybody. So the reason I want to do this, I'm not done with dimensional analysis. You have two other handouts on dimensional analysis, handout 8A and 8B. But before that, I actually don't want you doing any more calculations without using the right significant figures. So I have to do a little segue into significant figures, and that is what we have right now. Okay, so because we're starting to do numerical calculations, I want you to get some good habits from the get-go, okay? So if we could just keep moving on with this and calm down and just listen. All right, so we're talking about significant figures, and this sort of leads into concepts of precision. And also we sometimes talk about at this time accuracy. But accuracy really means how close the value is of a number to the correct value. So accuracy has to do with how correct a value is. And we're not really talking about that right now. What we're really talking about today with sig figs has to do with precision, which is really how well, in other words, to how many places, how many decimal places do you know a number? And, you know, scientists go crazy over this. We really care about this. And so it pains us when students see a number like 1541 and they write it as 1500 or something like that, because the meaning to us is so clear that if you write a number and you show the ones place, it indicates that you have some knowledge of that ones place. You know, I remember I went to the doctor when I was pregnant with my son, who is now, 28. And I can't remember the number of grams. They said that the baby weighed, let's pretend it was early in the pregnancy and the baby weighed 734 grams. And I said, I was so impressed. I was like, you know the mass of that baby within a gram? Because when you write a number like that, and you tell me that that ones digit is a 4, that tells me, it's not a 3 and it's not a 5. It is a 4. Or at least it's between 3 and 5. And I was amazed that you could tell that from an ultrasound. And you know what the doctor said to me? He said, oh, that's plus or minus 100 grams. I just looked at him and I said, didn't you go to school and learn about significant figures? Because the way he really should have expressed this number was 700 grams, because he really didn't know if it was 600 or 800. By telling me it's 734, me being a science person, I know that the uncertainty is in the last digit, okay? So we really care about certainty and uncertainty. And I think that guy hated me, but whatever, that's his problem. Oh, look, I have to get rid of this. I already told you about this. Cut. This is the same special problem I already told you about, so just forget about it. Okay. So anyway, if I weigh something like a rock, and I weigh it on a cheap plastic scale that I bought at the dollar store, okay? And it tells me that it weighs 22 grams. And then I take that same rock across town to Rhode Island College, and I weigh it with a beautiful a balance, what do we call it? Fine lab balance. And it comes out to 22.3574 grams, okay? It's the same rock. And you look at these two numbers, okay? And you say to yourself, is this the same number? And if you're me, you say, no, it's not, because this number, this 22 grams, implies that the number is between 21 and 23, that the uncertainty is in the units place, right? This is the units place. But this number, 3574, implies that the uncertainty is in the 10,000s. I don't even know how to spell that. Place. So this one is much more precise. Let me write it better. 22.3574. This is more precise. This is less precise. And when a scientist writes a number, the precision is implied with the way they write the number. So we would look at these two different numbers and say they are really not the same. The assumption is that the last digit is uncertain. So like I said, this 22 is between 21 and 23, maybe even 20 and 24, not really sure. It's like plus or minus 1 or 2 grams. But this number is like plus or minus 0.0001 or plus or minus 0.0002 grams. In other words, it could be 0.0001 higher, 22.3575. It could be 22.3573, but it's not going to be 21 or 23. You see the difference? I hope so. Okay. Anyway, so implicit in the way we write numbers is how well that number is known. Okay. And the way, okay. And another thing we have to do or think about is when we do calculations, we have to have a way of keeping that precision. We can't know the result of a calculation more precisely than the numbers that we used to do the calculation. Yeah.
Last number always has twice, you always add a uncertain number at the end. Why not just not put it in uncertain? Why not?
Well, we're going to have to stop somewhere. So what would you do? Have one less number and have the last number be certain? It's just the way that we've been doing it forever. So we chose to do it that way. Yeah, I guess we could have done it the other way. But when we do calculations, we need to keep the correct precision. And so, because you can't know the result of a calculation better than the numbers that you used to get that result. Okay, so if I do an example here, here's, let's say, a graduated cylinder, okay? Has numbers on it going up, whatever. And let's say we start with some water in the graduated cylinder. So it's filled. And then we add that rock. Hold on. I'm gonna calculate the density of that rock. So I put the rock down here, and the level of the water was over here. Now the level of the water is over here. Okay, anybody know what we call this? We have what we've measured the volume. We call it by water displacement. We've displaced some of the water, and the height increase of that water is, so this difference here, I'm going to draw it a little higher just to make it more exaggerated. Okay, so let's say that this is 96 milliliters and this is 87.5 milliliters. So that means that the volume of the rock is the difference between 96 and 87.5. So I do my math and I get 8.5. That's the volume. And then I weigh the rock. We already did that. And I only have the cheap balance that I bought at the dollar store. and I have 22 grams. So the density is the mass over the volume. So it's 22 grams over 8.5 milliliters. Now, if you do that on your calculator, this is what you get. And the unit would be grams per milliliter, okay? Is that what I should express my answer as? You know, clearly I only know the mass of the rock to two digits and the volume of the rock to 2 digits. How can I possibly know the density to that many digits? It's kind of absurd, really. It's just not believable. Yeah, okay. So anyway, so that's really, we have to have a set of guidelines or rules that we use when we do calculations that allow us to express an answer to a credible number of figures. Okay, we have to realize that we really don't know this answer this well. We don't know the density to this many figures. It's really just, it's absurd to think that you did, because you only know these numbers to 2 digits. Okay, so let's move on to these rules. Now, a lot of what I'm saying here, I found this guy, Tyler DeWitt. Honestly, the first video, he looks a little drunk. He looks a little intoxicated. But he's really good, and he goes at a reasonable pace, and he's got several videos. This is the first one. You don't have to copy that down. I have the link on Blackboard under chapter 1. And if you want to learn, you know, go over some examples, he's pretty good. But anyway, what I have to do is 2 things. I have to give you, basically, the first thing is I have to tell you, how do you count the sig figs? We call them sig figs, these digits that we get to keep, the digits that are the right precision. How do we count the significant figures in a number? And number 2, how to correctly use these sig figs in calculations so that we end up with the number of digits that correctly reflects the precision of the number. Okay, so I'm going to start with, these guidelines are in activity 6, so you actually have them written down already. All non-zero digits are significant. So let me just give you one example. I have a number 1.2578. I count the number of digits. 1, 2, 3, 4. There are 5 digits, so there are 5 sig figs. I write that as 5 SF, okay? Okay, so what if I write this number down? Oh, I don't want to do that. Not yet. How many sig figs in that number? 4 sig figs. 3.275. How many? Okay, so what about, all right, that's good enough. Now let's move on to when we have zeros, because zeros are the problem. Interior zeros, that is, are zeros that are between 2 numbers, are significant, okay? So for example, here I have an 1.2703. Just because this number happens to be a 0 doesn't mean it doesn't contribute to the precision of the fact that that number is known to 4 decimal places. So interior zeros are always significant. So I have 1, 2, 3, 4, 5 significant figs here. S5 SFs, okay? 1042, 1042. How many sig figs in that number? 4, okay? All right. Now we come to the problem. Numbers sometimes are written with leading zeros. In other words, like this number starts out with, well, of course, we have the 0 here, which a lot of people wouldn't even bother writing, which is fine. I write it because I think maybe I won't see the decimal place, right? So I put the 0 there. But this number here, how would you write this number in scientific notation? .48, you'd have to move the decimal times 10 to the -2. That is correct, okay? Now, when you write it that way, notice it doesn't have that leading 0, okay? That leading 0, the only reason it's there is to hold the place, is to tell you that that 4 is in the first 4 is in the hundredths place, okay? So you have to put a 0 in the tens place. It's just to show you where the decimal point is. It's just as a placeholder, okay? So leading zeros do not contribute to the precision of a number because they're just holding the place, okay? So leading zeros are not significant. So this number has only 3 significant figures, okay? And anytime I have 0.0000327.065, what about that? How many sig figs there? 1, 2, 3. This is an interior 0, 6 sig figs, correct. Okay. Now, here is a difference. Trailing zeros. These are zeros. Oh, yeah, you don't have to come up and tell me. That's fine. Give me the HOD tomorrow. What's your name? All right. Trailing zeros are significant if the number has a decimal point. All right. So here, what we're saying is if you are careful enough to write a number and you actually put a decimal point, that communicates to everyone else that you have to believe all those digits. All right. So it makes a difference whether the number has a decimal point or not. Let me give you, this is best seen by example. So I'm going to write a couple of examples. Here's one example. Here's another example. And here's a third example. Okay. Now, this is a case where I was careful enough to not only put a decimal point, but to add 2 extra zeros after that decimal point. So I am communicating to you that this place here, the hundredths place, is that's the digit that has the uncertainty, but we say that that is the last digit of any significance, okay? Because I have bothered to put a decimal point here and to write 2 zeros after. So all of these trailing zeros are significant, and there is 6 sig figs in this number. Now, this number falls under this second bullet point here. Trailing zeros in a number without a decimal point are ambiguous. So it's like, I'm not telling anybody that these zeros are too important, but maybe they are, maybe they aren't. If I really knew they were important, I'd put a decimal point like I did here. And how many sig figs does this number have? 4 sig figs. I didn't put it here. So in my classroom, this has only 1 significant figure, that 2. Those zeros are ambiguous. They could be interpreted either way, but let's make it a rule. Let's make it that we don't count them if there's no decimal point. So trailing zeros are not significant unless the number has a decimal point. So that's a bit of a confusing rule, but you get used to it. Okay, so now let's go through this. How many significant figures are in these numbers? What about this one? 6, I heard someone say it. That is absolutely right. This is a trailing 0 in a number with a decimal point. So that's significant. This is an internal 0. Okay. What about this one? 7. So the ones that count are all of these. What about this one? All of them count. What about this one? All significant. What about this one? Yeah, that's also 3. What about this one? 1. And what about this one? Okay, now we have a number here in scientific notation. It has a decimal point. All four of these numbers are significant. It's trailing zeros, but the number has a decimal point. And what about this one? 4. Now, when you put it, yes. No, it has a decimal point, so the trailing zeros are significant. No, there isn't. I could have written a number like this without a decimal point, without a zero after the decimal point. When you know it to the nearest tenth of whatever unit that is. Okay. Yeah, let's skip this. It just opens a can of worms I don't feel like talking about now. All right, so how do we use these things in calculations? Okay, so this is on the this is also, I think it's on the next page, but I prefer to actually go over a calculation and then talk about the rules. And I'm actually going to talk about addition first, addition and subtraction. And I'm going to show you how this works by lining these numbers up so that you could see, you know, the places of each one of these things. So if you line them up, this is what it looks like. And what you do when you're doing addition, you have the first number is known to the nearest 100th place. The second, third, and fourth. Wait, let me get. So these numbers are known to the 1000th place. But when you are adding numbers and one of them is known to fewer places, that number is going to determine your precision because that is the least precise number. So what I do is I would sort of mentally draw a line here and say, what I'm going to end up doing is only keeping the 100th place. Because this guy has the least decimal places and it's only known to the 100th place. So I would do this arithmetic on my calculator. I wouldn't just add it up in the columns, and you would get 9.788. Okay. But the fact that you only know one of these numbers to the 100th place means that you are going to round to the 100th place, which I don't know how to spell. So I have 9.788. I look at this number here on the side, the next number. If that number is 5 or greater, I round up. 9.79 is my answer here. Okay, so you notice for addition and subtraction, and this is the rule, when the result carries the same number of decimal places as the quantity with the fewest decimal places. Yes, your question. Yeah, the book has a much more painful rule about whether this number is even or odd. You know, nobody does that. Everybody, a 5 and up is round up, a 4 and down, you round down. Isn't that what you learned in high school? Yeah, so that's what you can do. That's my rule, Cooley rule. Yeah, I actually, I was going to mention that the book has a slightly more confusing rule, but anyway, okay. So, and here, that's actually what I wrote here, that when you're rounding to the correct number sig figs, right, it just says what I just said. So it's a little less confusing than, I wrote it here, simpler than OpenStax. So that's what we use. All right. So, and actually for subtraction, it's the same as for addition. You use the number of decimal places in the number that has the fewest decimal places, and that tells you what you get at the end of doing that addition. Okay, multiplication and division is actually an easier rule, much easier, and that's what we mostly do in this class, is we multiply and divide. So what we do is we simply count up the sig figs in each of the numbers. How many sig figs in this number here? And how many sig figs in this number here? And we keep the least, the smaller of those numbers in the result. So when you do this division, your calculator says 2.558, and we will keep only 2 sig figs. So we will round this to 2 sig figs. And so we will end up with 2.6 because this number is 5 or above. See that? All right. So that was C. Let me go to B. I did C first because C was easier. B is a little harder because there's really 2 calculations in this calculation. And one is a subtraction. So I'm going to do what's in parentheses first, as you always do. And let me show you why I'm doing this, okay? So this is a subtraction, like an addition. I line it up, okay? And I say, oh, okay, this number is significant to the tenths, and this is significant to the hundredths. So for addition and subtraction, we look at decimal places. Let's put a little line. I'm going to only be able to keep the tenths place. Now, what this comes out to is 0.15. This is what the calculator says. So if I was going to express the answer just for the numerator, how would you express that answer? What would the answer be for the numerator? Well, you'd round up to 0.2, right? Right. But if you simply did that and you did your next calculation rounding up to 0.2, you would actually end up with the wrong answer. Let me show that to you. And let me show you this rule. If you have a multi-step calculation, to avoid what we call rounding errors, it is best to round only in the final answer. So this is what Dr. Cooley would do. I would keep both of those numbers, but I would underline the last number that's significant. I know that I should have rounded this number to 0.2, but if I did that, I would change my result when I divide by the 23.85. So let me show you, when I do this math and I take 0.15 over 23.85, I get the answer on my calculator. This is what it says. What should my answer be? How many sig figs in the top number? 1, because I've shown you by underlining it. How many sig figs in the bottom number is 4. So my result should have 1 sig fig. So I should round this to 0.006. All right. What if I left it as 0.2? If I did that, and I did that on my calculator, I'd end up with 0.008. And you could see that this is different from this. This one is wrong and this one is right. But I'm going to tell you something else. I never take off for that. If you rounded to the correct number of sig figs before you did your math and you got a different number because of that, you shouldn't do it. And hopefully if you're a science major, you would do it this way. This is really the correct way. Okay. And you'll see me doing it this way whenever I solve a problem. Okay. And a lot of times when a student gets an answer that's a little bit different from my answer, and yet I marked it right, it might be that they had some round off error there, but I'm not gonna get too crazy about that. I do want you to use the right sig figs. I do count it to some extent. Anyway, I hope you learn to do all this correctly. Pay attention to your sig figs, please. And next time I'm going to do a few more examples of dimensional analysis. You can look at 8A and 8B. That's what I'm going to do some of those problems next time, but I can't do them all. We're going to move on to chapter 2 on Tuesday. And we have a quiz on Thursday of next week. So please get me those academic honesty statements over there on the end. And I did give you some extra problems for practice. I don't collect these problems, but I will post the solutions today. So you want to do more problems? That's great. Yeah, all right, have a good one. Hi.
Go ahead, no, you're good, go ahead.
Question about the last one, why was it only rounded to 1/7?
Because 23.7. No, well, but with subtraction and addition, it goes by decimal places, not by the total number of sig figs. Right, the rule for addition and subtraction is to look for the number with the fewest decimal places. Right, so it's a different rule, yeah.
For this, the hissing sound.
Oh, that's not anything.
Oh, okay, all right.
Yeah,